Welcome to the ENME 351 video lecture series. This is part one of a three-part installment in which we'll explore waveforms and signals. In this lesson, we'll take an introductory look at various signals. This slide can effectively serve as an outline for the entire course. We're sensing some data or some information with a sensor or a transducer. We're conditioning that information and ultimately sending that through an analog to digital converter such that we can convert from the analog world to the digital world, which is required for the communication and processing with a microcontroller or a microprocessor. From that microcontroller or microprocessor, we send that information to a DAC, a digital to analog converter, because we're ultimately trying to affect the world, trying to both sense it and affect the world. So from our DAC, we may do some more signal conditioning and then ultimately sending that information to an actuator or a transducer to affect or actuate something in the real world. And what's important to realize here is that within all of these red lines, these are known as signals. So there's information being transmitted from each block across the red line, across a signal to another block here. And signals are associated with the transmission of information. So this might be a DAC voltage, it might be a bit number, it could be any type of information associated with my mechatronic system. So if we want to explore systems as a whole and performance of these mechatronic systems, we need to set some metrics and some parameters by which we can compare the performance of one system to the next. Two of the signal attributes that we'll discuss most often will be that signal's amplitude and frequency content. The amplitude of the signal is going to be its size. It's going to be the magnitude of the signal. And the amplitudes of these signals that I'm working with is going to affect things like the range of the sensors that I'm using in my system. And it'll also define things like the number of bits I need or the range on my analog to digital converter, let's say. So I need to appreciate the overall amplitude of my signal, the size of the signals I'm working with, and how that drives the design of my system. The signal frequency, on the other hand, this is describing how the signal is changing with respect to time. And that'll certainly affect things such as the bandwidth of the sensor that I'm using in my mechatronic system. The frequency of a signal will also dictate how fast I need to sample a particular signal such that I can properly analyze and utilize that signal in the digital domain. A waveform describes the particular shape and form of a signal. And we can classify waveforms in a number of different ways. In fact, so far we've discussed classifying a waveform as an analog waveform, a discrete waveform, or a digital waveform, where an analog signal, of course, is continuous in both time and amplitude. I have time on my x-axis, and my y-axis might be something like, say, y of t. My discrete waveform, I'm going to be sampling in discrete chunks of time. So I'll have discrete values along the time axis. However, along my y-axis, I can still occupy any value. And a great way to think about the discrete waveforms is that in the limit as delta t goes to 0, so delta t is my sampling interval, and as the limit of delta t goes to 0, my discrete waveform, y bracket n, will be equal to my analog waveform, y of t. For the digital waveform, I'm sampling in both discrete packets of time as well as discrete quanta along my y-axis. So my sampled signal is only permitted to occupy specific values with regards to time and amplitude. Let's consider then the signals we might encounter when talking on our cell phone. Well, when I'm talking into the phone, that speech will certainly be an analog signal. The signal arriving at the microphone as well as the signal output from the microphone, those will be analog signals. Inside the cell phone, I'll have a sample and hold circuit. And this circuit will sample that analog signal coming from the microphone, which would result in a discrete signal. And then finally, I'd have that sampled signal going into an ADC, into an analog to digital converter, where the output of the ADC then will be a digital signal. So in this sense, in the example of a cell phone, we have the full range from analog to discrete to digital signals occurring. The most basic type of waveform that you'll encounter is going to be a static waveform. And static waveforms, these are waveforms that are not changing, or they're changing so slow that it's really not affecting the performance of your system. The static waveform will look something like a straight horizontal line, where the amplitude along my y-axis would be described as A0. And I could describe this static waveform by the equation here, y of t equals A0.